Hello everyone. In today's session, we are going to discuss some example for a scenario-based example for Turing machine construction. So first question is, Jay visited a store to buy some gallon of milk and bread. So a person is going to buy milk and bread, and first she buys milk. So M come first, followed by bread, which is twice the quantity of milk. So bread is twice the quantity. If milk is of n number of milks are like n gallon of milks are bought, then 2 power n quantity of bread is bought. Okay, so m followed by b, and b is twice the quantity of m. So this is the scenario. Okay, so the language for generate the language accepting for the scenario is L is equal to, you can use any variable. It need not to be M and B. You can give A and B, A for milk and B for bread. Okay, any kind of things are acceptable. So here my language consists of M and B. So N number of M followed by 2N number of B's, and N is greater than or equal to 1. So this is my language accepted by the Turing given scenario. So this is the language acceptance. Now you're going to design a Turing machine for the mention by mentioning the transition rule generated language. So I want to construct a Turing machine with transition rules, draw the transition diagram, transition table for the Turing machine. So I have two questions covered up in this place. So I always prefer easy way of doing it by constructing the transition diagram. Then I'll show you how to write the transition rule for it and how to write the transition table for it. Okay, so the transition diagram is like this is the scenario, and the logic I'm going to follow is when I have n number of m's, I'll be having 2n number of b's. Okay, and I just use this as the blank representation, some hyphen as the, okay, this as the blank representation. Okay, so I'll be having m followed by 2m. So it means that like when it is mentioned in the power of thing, it is not multiplication. It is not multiplication in order, right? So here the number of m's, like when I take the number of m's as 1, 2, 3, then b will come as for single m, you will be having two b's following each. For the next m, you'll have two b. For the next m, you will have two b's. Okay, if it is at this scenario, we have to accept it. So what my suggestion is, I'm going to cancel the first m, check for a b. Whenever b forms, I have to cancel two b sequentially. Come back, take the next m, go and check for next two b's. Next m, next two b's. When I'm coming to check for the next m, I don't have a m here. Okay, it is all cancelled. Now I have to verify whether all the b's are cancelled. If it is perfectly cancelled, then we can say that the given input is accepted. Okay, so this is the scenario, and this is the logic that I'm going to use over here. So I'm going to have the first state, transition state in Q naught for finding an n. Okay, so in Q naught state, if my input is em, I'm going to Q1 state. So I'm going to cancel this n. I can use any symbol for cancellation. For my consideration, I'm just going to use x. Okay, so m is cancelled as x and move right. So here first m is cancelled as x, move right. And whenever you have a cancellation, better to have a change of state. Now, what is the next step? I cancelled one m, and for this single m, I have to find two b's to be cancelled. Okay, so in Q1, for any number of m that lies in between, we are just moving right. And once we found the b, cancel the first b. So this first b is cancelled to another symbol y. I just use different symbols here to check or to cancel an m and to cancel an b. I'm going to use different symbol for our representation. Okay, and go to Q2 state. Now in Q2 state, I have to find one more b. See, for a single m, I'll be having two b's in a sequence. Okay, so I have to take this b, cancel it to y. I have to take this b also, cancel it to y. And go to Q3. Whenever you have a cancellation, better to have a state change. Now, what is the next step? For one m, two b's are cancelled. I have to repeat it for all the number of m's, right? So now I have to come back to find the next m. So it is in left side move. Till now I have taken one m, move right, right, right until I find a b. And whenever I have a B, cancel two Bs in parallel. Okay, now I have to repeat the procedure for all the remaining ones. So I'm going to come back. So I'm just going to have a transition back over here. I'll put a self loop in Q3 where I'm going to come back after cancelling this B to Y. I have to come back till this X. Since X denotes it is the cancelled M. So in between I may have any Y, move left, or if I have M, move left. Okay, either Y or M, we are not bothered about it. We are just going to move left, left, left until we find the X. And once we find the X, what you're going to do? We are going to repeat the same procedure. I'm going to take this M, cancel this M, check for a B. Okay, check for two B's in sequence. Now, when I have an X here, X will remain as it is. X will remain as it is. We move one step forward. Okay, one step right side to Q0 state to start the process. Okay, what it do in Q0 if the input is M, it cancels M to X and I have to find a B. So in between I can have any number of Y. It doesn't matter. We keep on moving right, right, right until we find a B. In Q1, if we find a B, cancel it to Y, go to Q2 state. In Q2, if there is a B, cancel it to Y, move left. So this process is iterated for any number of M's. For n number of M's and 2n number of B's, this process is repeated. Now what do we do after cancelling this? We are going to come back until you have an X. Okay, so now you have an X here. So after this, what is the next step, Ma? When we make one step right in Q0 state, when you're trying to take the next input, since I have only two M's and both the M's are cancelled, when I am trying to take the next input in Q0, I'll have Y. I don't have an X, right? So in Q0, when the input is Y, it means that all my inputs are cancelled. I don't have any extra M to cancel. So in this case, what is the next step? I'm going to verify whether all the B's are also cancelled. Okay, so this Y will remain as it is, move right to a new state Q4. In Q4, we are going to verify until you have a blank symbol that all the elements are cancelled. So Y will remain as it is. We keep on moving right, 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 right until we find a blank symbol. Once we find a blank symbol, it means that the input is properly verified. We are going to Q accept state. Got it? So this is your final transition diagram. Okay, so whenever your input belongs to the language, the input will be accepted. Take one M, cancel to B. Take one next M, cancel to B. We have to repeat it for all the M's, and when all the M's are cancelled, we are going to verify whether the B's are also cancelled. Okay, so now what you're going to do, acceptance is defined. We have to check for the rejection state too, right? How you're going to find the rejection state? In Q0, when the input is M or Y, we have all the transitions. In Q1, like when you have an excess number of M's, okay, two possibilities they are there. One is when you have excess number of M's, another one is when you have excess number of B's. When you have an excess number of M's, see when I have 2M and 2B's alone. For this M, this B will be cancelled. For this M, we don't have a pair over here, right? So in Q1, instead of a B, when you have a blank symbol, then that is a rejection. In Q2 also, instead of a B, if you have a blank symbol, that is also a rejection state. Okay, so these two are the scenario when you have an excess number of B. Okay, so transition of Q1 when the input is blank, we are going for Q reject state. Transition of Q2 when the input is blank, we are going for Q reject state. Now, when you have excess number of B's, see here, 1M followed by 3 or 4 B's. So this M is cancelled and these two B's will be cancelled. So you'll have X, Y, Y, B, B, B. When I am trying to take the next input, I don't have next input, it goes to Y. So Q0, when the input is Y, it means that all the M's are cancelled. Now at this place, while verifying, we go to this Q4 state. Now in Q4, if you have any extra number of B's, then that is also rejection state. Okay, in transition of Q4, when you have extra number of B's, it is also Q rejection state. Okay, so this is your transition diagram. representation for the given scenario. And next step is we have to either go ahead with transition table or transition function. When you want to write the transition function, just write it like this here. Okay, so I'll write for few, I won't write all. I'll just write for this Q naught state and all. Remaining things you can copy it. Just know the scenario of how to write it. Transition function for this will be written as transition of Q naught when the input is M. Okay, we are going to Q1 state. I'm just taking this transition. Q naught when the input is 1, we are going to Q1 state by making this M to X and move right. And transition of Q1, the self loop condition. You have two self loop, right? When the input is Y, we stay in Q1 state itself. Y will remain as it is, move right. Transition of Q1 when the input is M, we stay in Q1 itself. M remains as it is. We are making a right side move. Okay. So similarly, you have to write the transition for all possible transitions like Q1 when the input is capital B. Q1 when the input is capital B. We are making a transition to Q2 state. And this input B will be converted. The B in the tape will be converted to Y. And we are making a right side move. So this is this transition. And Q2 to Q3, transition of Q2 when the input is B, we go to Q3 state, B will be converted to Y and we are making a left side move. Okay, so this is how you have to fill all other transition including the rejection one. Perfect. Now we know how to write a transition rule, how to draw a transition diagram. And next thing that you want to do is to do a transition table. So transition table for the scenario is, I'll do it here. It's two-dimensional, dear. See, for NFA or DFA, we are able to construct a transition table, but for push-down automata, we cannot do it. The reason is the transition is based on a state, a stack element, and an input. There are three dimensions. When you want to create a transition table, it will go as a three-dimensional tape, a three-dimensional structure. But when it comes to Turing machine actually reads an input, like it has some set of states and it reads the element on the tape. So one side you will be having state, another side it will be your tape symbol tau. Okay, so with these you have the transition or the movements. So we can fill it. Now the states are Q0, Q1, Q2, Q3, Q4, and Q accept. These are all the states where Q0 is the starting state, Q accept the accepting state, and you have Q reject also, you can mention that. Now Q0 and the tape elements are, initially tape will have M and B and the blank symbol, and later on M will be cancelled as X and B will be cancelled as Y. So all these symbols has the possibility to be written in a tape. So you have to write for all possible criterias. Okay, so Q0 when the input is M. Q0 when the input is M, we are going to this Q1 state and M is replaced as X and we make a right side move. So you have to fill all these three elements inside. Now Q0 when the input is B, Q0 on B, you don't have any transition. It might be a rejection state. Now Q0 when the input is, like initially when you have only B's in your input, it has to be rejected too, right? So Q0 when the input is B, we go for Q rejection state. Either move right or left, it doesn't matter. And Q0 on the blank is also rejection. Q reject. Okay, so Q0 when the input is X, you don't have any transition. When the input is Y, Q0 when the input is Y, we have a transition to Q4 state. So Q4, Y remain as it is, move right. Okay, now Q1 when the input is M, you don't have any, M you have a transition. See Q1 when the input is M, we have a self-loop condition. So we remain in Q1 state itself, M will remain as it is, move right. Now Q1 when the input is B, you have a transition to Q2 and B is converted to Y and we make a right side move. And Q1 when the input is blank, we are going for this Q reject state, right? All the transitions of Q reject. And B1 when the input is X, you don't have any transition. And Q1 when the input is Y, you have the self loop condition. So Q1 remains in Q1 itself, Y remain as it is, move right. Okay, so Q2 on input M, you don't have any transition. When you don't have any transition, you can just make it as null. For acceptance state, you don't have any transition. And similarly for rejections also, you don't have any transition. And you don't have any transition, just put a blank of it. Okay, so Q2 when the input is B, you have a transition here. It goes to Q3 state. B will be converted to Y, move right. Okay, so complete the entire table from the transition. This is just to give a gist that this is how we construct a transition table. Okay, I hope you understand how to construct a transition diagram, transition table, and a transition function. Okay, while writing the transition function, you just make sure that you know about the tuple notations. Tuple notations are nothing but like what all the element that you get Turing machine, like you can uh, use to represent a Turing machine. You have this Turing machine as set of states, set of input symbol, the elements that can be written on the tape, transition function, starting state, blank representation, Q accept state, and Q reject state. So these are all the tuples that are used to represent a Turing machine. So here the set of states are Q0, Q1, Q2, Q3, Q4, Q accept, and Q reject. Your input symbols are M and B. Your input is made up of M and B, right? And the element that can be written in the tape is M, B, blank representation, X, and Y. Okay, so you have to fill all those things. When you write all those things, so this is your transition function, del. Okay, so this is your formal way of representation. Like sometimes instead of giving it as transition rules and all, they will ask you to write the tuple notation. So when they are asking to write tuple notation, you have to write all along with this transition function. Okay, so design a Turing machine done, transition diagram, transition table done, and it is a computable device or an acceptor. See, when you call a Turing machine as a computable devices is when it is doing some computation process like addition, subtraction, multiplication, and all like some calculation like your calculator. When you are designing a Turing machine to perform some of the mathematical operation, then we call that as in computable devices. And the term acceptor is very important. See, we have an acceptance state. When the input belongs to the language, we are going to accept it. And when the input doesn't belongs to the language, we are going to reject it. So we have been defining this acceptance and rejection state. And when the input is given to the Turing machine, it will either accept or reject it. Okay, so that for the given problem, your Turing machine you have designed is an acceptor. It is not a computable device, it is an acceptor. When you have this addition, subtraction, multiplication problems to be solved, then that will be your computable devices. Okay, so in this example, you're going to verify whether the scenario is satisfied or not. Okay, so it is just an acceptor. Now we have to simulate a Turing machine for bread purchase. So it is nothing but how to do an instantaneous description for some input. I'll do one thing. I'll just erase this table. Okay, and I'll take that given example. Given input example is milk followed by 3 bread purchase. B. Okay, so when you want to check whether this is accepted or not, you have to simulate your Turing machine and write your instantaneous description for it. This is my blank representation, right? Now starting from this place in Q0, when the input is X will be converted, sorry, M will be converted to X, and we are making a transition to right side to Q1 state. So this is how exactly it will done. Okay, step by step simulation is needed. Now in Q1 when the input is M, Q1 when the input is M, we are making a transition to next right side move in the same state. I'll just do it separately. For one example, I'll show how to do it. X, this M will remain as it is. We are making a right side move to this place in Q1. Okay, so in Q1, if the input is B, B will be converted to Y. So at this place, this B will be converted to Y. Remaining symbols will remain as it is. And we are making a right side move to Q2 state. Okay, so Q2, when the symbol is B, what it do? B will be converted to Y and we are making a left side move here. So this is called simulation, step by step showing how exactly it is working. So this B will be converted to Y and we are making a left side move to Q3 state. Always remember the transition here. So in Q2, after cancelling this B to Y, we are making a transition to Q3 state. And in Q3, we'll be coming back. So one cycle is completed, right? So for this cycle, okay, I'll just complete the entire portion and I'll tell you. So in Q3, we have to make a left side move until we reach this X. So this will remain as it is. We just move this side to Q3 on X. And Q3, when the input is X, what it do? Q3, when the input is X, we start the process from Q0 state. I'll write it here. This is the state structure right now. All blank symbol. Now it'll start the process from Q0 here. So Q0, when the input is M, M will be cancelled to X and we are making an right side move to Q1 state. In Q1, we have to move right until we find a B. So for all your Y's, we keep on moving until we find a B. So we'll have a lot of moves here. Now, after reaching this place in Q1, when the input is B, okay, this B will be converted. See, in Q1, when the input is B, B will be converted to Y and we are making a we are converting that B to Y and we are making a right side move to Q2 state. Okay, so for each M, we should have two B's in parallel. Okay, that should occur in sequence. Now, for this M that we have cancelled now, we have only one B. Okay, in Q2, you don't have B. We directly go to this empty state, like blank symbol. So in Q2, when you reach this blank symbol, what it means, we are going for the rejection state. Okay, so the tape over here will remain as it is. We'll either move left or right and we go for this Q reject state. Okay, so this is how you write the transition. So with this, we can say that when you simulate the Turing machine for this condition, the input is rejected. So the final justification, you have to write it once. Okay, so now the next important thing is, in the question, if it is mentioned it as instantaneous description. Okay, so instantaneous description is something like where you have to write this, you have to simulate this element as a whole in a single line. So that is called instantaneous description. So you have to write the element in the tape as it is. So M, M, B, B, B blank symbol will remain as it is, and wherever your reader head focus on, in the prefix you have to write the state. Okay, so for this the instantaneous description is you have X and you have an M to the prefix of it, like reader head focus on this M, right? To the prefix of it, I have to write this Q1 and the remaining elements will remain as it is in the tape. Okay, so this is the first step, this is the second step, and third step, write the instantaneous description. You have X, M, your reader head focus on this place, right? Write it as Q1, B, 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 blank representation. Okay, so similarly, you have to write for all, and from this, we can say that this is the first step, and from this, you are able to write the second step, right? So this called move of a Turing machine. So from this step, the next step is instantaneous description of next step is this one, M, B, B, You have three B's, right? Three B's followed by blank symbol. And from this, the next instantaneous description is this one, right? EXMQ1 BBB blank. Okay, so this is called ID description. You have to write the ID description for all the remaining tape structure. Okay, in question, if it is mentioned as write the instantaneous description for the given input, you have to follow this sequence. Okay, and sometimes we can write that starting from this place, you are able to reach this place. The instantaneous description for this place is EX, X, X, Y, Y, and your redirect focus on this place, right? You have Q, reject, and Y. So this is the instantaneous description. So you can write that from the starting state Q naught M M B B B blank, you are able to reach the last step, that is X X X Y Y Q reject Y blank on multiple steps. So star denotes on multiple transition, on zero or more transition, you are able to reach this state. Okay, so this is how you write your simulation of Turing machine on an input and an instantaneous description. Got it? So most of the things are done. And finally, we have this criteria called encode the constructed Turing machine in a binary language. Okay, so encoding is nothing but, like we said, right, like Turing machine has the capability of solving all the problems that we solve in a real time. And when you want to simulate this Turing machine, that simulation is also a problem, right? It is also a task. We are able to simulate a Turing machine inside a Turing machine too. So that is called encoding. Okay, so encoding of Turing machine is a bit complicated one. Like I'll just do step by step. When you want to encode the Turing machine, the first step is to write the tuple notation. Okay, so we are going to convert these tuples directly into a encoded structure, Q naught blank representation, Q except alone. Okay, so while writing the tuples, just write the 7 tuples alone. So now what I'm going to do now, I'm just going to have either a 0 representation or 1 representation for encoding. So for my example, I'm just going to split this elements. I'm going to use 0 as my representation. 0 is to represent my elements and 1 as a delimiter. Okay, so to separate all the elements, I'm going to write my transition as Q followed by 2, 1 as a delimiter, sigma followed by 2, 1 as a delimiter, tau 2 ones, Q naught 2 ones, blank representation 2 ones, Q except state. Okay, so now this is a basic one. I'm going to use 2 ones as a delimiter between each and every component of each and every element of my Turing machine tuple. Now the next step is in Q, how many elements I have? In Q is the set of all states, right? In Q, we have Q naught, Q1. All right. Q is represented as you have Q naught, Q1, Q2, Q3, Q4, Q accept, and Q reject states. Okay, so for each state, I'm going to give the values as a single 0 for Q naught and 2 0 for Q1, 3 0 for Q2, 4 0 for Q3, 1 2 3 4 5 zeros for Q4, 1 2 3 4 5 6 6 0 for Q accept state, 1 2 3 4 5 6 7 0 for Q reject state. Okay, so now I'm going to split all this. Okay, so these are all the set of states, right? That is the one that need to come in first. And one act as the delimiter. So between each and every element, I'm going to make this one. So the sequence for this is written as 0 followed by 2 zeros, 3 zeros, 3, 4, 1, 2, 3, 4, 5 for your Q4 state and 6 zeros for Q accept state for Q reject state. Okay, so this is my first element Q. And next, this is followed by sigma. And sigma is my input. My input consists of either milk or bread. And I use single zero to represent milk and two zeros to represent bread. So I can rewrite it as 1 0 separated by 1, 2 zeros. Okay, so this is my sigma portion. While writing it, make sure you are writing it properly. These are all my Q and these two are my sigma separated by tau. And tau consists of bread, milk, blank representation, x and y. Right? For bread, like you can use the same symbols written over here. I use 0 for milk and 2 zeros for bread. And for blank symbol, 3 zeros. For x, 1, 2, 3, 4. For y, 4, 5. Okay, so how I'm going to write the transition? For N, for B, for blank, and for X, and for Y. Okay, so between these double ones lies your tau. Similarly, you have to fill the entire transition. Okay, so next you have transition that I'll just give a break. Okay, so I'll just add it later. Followed by two ones, you have Q naught and you have single zero to represent Q naught. Followed by blank symbol. For blank symbol, you have three zeros to represent blank symbol. Separated by double one. So this is your blank representation. And this is your, this is your Q naught state. And this is your blank representation. And for Q accepting state, you have 6 zeros for Q accepting state. 1, 2, 3, 4, 5, 6. So this is the entire way of encoding technique. Okay, I hope you understand this. Now for transition, I'll tell you the single transition alone I'll explain, like it will be time consuming and it will take a lot of space to occupy. So when you have a transition function, for each transition function, let us consider Q naught and the input is em. We are going to Q1 state by converting this em to x and move right. Okay, so now this transition is written as for Q naught, the corresponding representation is 0. Separated by for M, the corresponding representation is another 0. Okay, and for this Q1, the representation is 2 zeros. And for X, the representation is for X, the representation is 4 zeros. 1, 2, 3, 4. And for the directions, you have to make the representation. For left move, I use it as single zero. For right move, I use it as 2 zeros. You have to write. Okay, so this is the encoding for the given transition function. Similarly, you have to write the encoding structure for all the given transition function, and finally you have to add it up in the place of your del. Okay, so separated by two ones, when you are able to do it in this del portion, then that is your final encoding structure. Everything will be in terms of zeros and ones, where your two ones is your delimiter and single one it belongs to the single component. The element actually belongs to the single component. And when they ask you to decode it again, just write the same representation. Okay, like after writing all those things, when you write the tuple notations like this, like Q0, Q1, Q2, Q accept, Q reject, and all, that is your decoding structure. Okay, so I hope you understand how to answer for a single scenario based question in Turing machine like this. So here I have covered up the maximum portion here. So like you'll have this encoding, simulation, checking whether it is in computable or acceptable devices, what is in transition rule, transition diagram, and how to write a language descriptions and all. Okay. Thank you.